So as with limits, derivatives, and antiderivatives when it was indefinite integrals, we had a bunch of rules, and we still have those exact same rules that still work. For instance, the first rule is, what can you do with constants? Well, you can pull them out front. The second rule is, what can you do with addition and subtraction? You can separate them and do each part individually. The third, fourth, and fifth ones here are new, so I want to make sure you understand those, kind of give you a little visual representation of what's going on. So what's the first one say? Imagine if we were trying to find the area beneath the curve from A to B of some function. Okay, so I want to find the area beneath the curve of this entire thing. So what is it saying we can do? What it's saying we can do is we can break it up at any point C in between there. And then what I could do is I could find the area from A to C of that function. And then what I can do is find the area from C to B, which would be that second area of that function. So what I can do is split it and break it up into two separate parts and integrate that as two separate pieces. In fact, what I could do is break it into as many pieces as I want, but that's what number 3 is saying, is go ahead and break it up at any point in between there, and you're still going to get the same answer as long as you integrate that first area, the second area, and then you add those two together. Okay, what's number 4 saying? Number 4 is saying, imagine if you found the area beneath the curve from A to A of a function. Well, think about it. You have a function value here. What's the area of that function? Well, there's no width. So if I did the width times the height, there's no width, so the area has to be 0. So if the limits match, all you have to do is circle those limits and then write the answer 0. That's almost always a trick problem on a test. It's going to be a function that's really difficult to integrate, and some students are going to spend a lot of time integrating it. They're going to plug in the top number, they're going to plug in the bottom number, and they're going to notice they always cancel out, they always equal 0. So all I do every single time, no matter what, is I always check those limits of integration first. The second they match, I don't waste any time. I circle those limits, I write the answer 0 and the answer blank, and that's showing enough work. Okay, so what's number 5 about then? Number 5 is a little more difficult to understand. Number 5 says the integral from a to b of f of x dx is equal to negative the integral from b to a. So how can we motivate that? Well, think about it. If you're taking the integral from a to b of a function, all of our x changes are getting, my x values are getting larger. So if I did any width here, let's imagine that I had a width of a piece of it. If I did this, the right endpoint minus the left endpoint, I would always, the direction that I'm traveling, always get a positive change in x. So my width would be positive, my height would be positive. But now imagine if I went from B to A. If I'm subtracting my x values now, the second x value would be the one that's further left. So if I did a further left x value minus a further right x value, that would always represent, going in that direction, would always represent a negative change in x. And so what we'd be getting there is a bunch of negative widths times heights, a bunch of negative values. So if I change the direction in which I'm integrating, instead of going from left to right, I go from right to left, all I've done is changed all my positive values to all negative values. Well, how do you change it back? Just integrate it, get that number, and then do the negative of it, the opposite of it. So for instance, if I went from left to right, I might get a positive 18. If I went from right to left, I would get a negative 18. It's going to be the same area that you're talking about, just a negative value. So how do you change it? Just plop in the negative and you'd be good to go. They're the same thing. So let's look at example 2 here. It says find the area of a region bounded by the x-axis in the graph of f of x equals x squared plus 1 on the interval from 2 to 3. Now I'm a visual person. I'm going to picture what the heck are they actually asking on this problem. You are not required to draw this picture at all. So x squared plus 1 starts off at 0, 1. When I plug in a 1, I'd have a 2. So here's the point 1, 2. If I plugged in 2, I'd have a 5. So here's the point 2, 5. If I plug in a 3, I'd have a 3 squared plus 1, I'd have a 10. So that'd be clear up here. That'd be like 310 up here, okay? And my curve looks something like that right there. So what are we asking for here? We're finding the area of the region bounded by the x-axis. Here's my x-axis. And the function x squared plus 1, that's this function right here, on the interval 2 to 3. So what I'm doing is trying to find this shaded area right here, the area beneath the curve of x squared plus 1 on the interval from 2 to 3. So how do I find the integral of the area of the region? I use the definite integral. So I'm going to do the definite integral from 2 to 3, that's the interval that they cared about, of the function, which was x squared plus 1, with respect to x. So instead of having to use shapes in geometry, because this shape is curved, we don't know the exact area of the shape, now we can use calculus to find the area of a curved shape instead of something like a circle or a triangle or a rectangle like we've always found. So how do I do it? Integrate it just like you would. Well, the integral of x squared using the power rule would be x cubed over 3. And the integral of 1 would simply be x. We would have our plus c, but because this is a definite integral, we don't need it. I am still going to put my bar there to say I still haven't evaluated it, and I need to evaluate it from 2 to 3. The way that I do that is I plug in the upper limit. So this would be 3 cubed over 3 plus 3. Then I subtract off the lower limit. Again, always put these in parentheses so you don't forget to distribute the negative. So this would be 2 cubed over 3 plus 2. I'm going to plug this into my calculator using those parentheses very carefully. Go ahead and do some now. I'm going to leave my answer as a fraction. I'm getting a simplified fraction in my calculator of 22 thirds is the area. Again, that would be units squared, but there are no units in this problem. It's not an applied problem, so the answer would simply be 22 thirds. Let's go ahead and take a look at that next example. That next example is evaluate the definite integral of 2t plus 3 cubed. There should be a parentheses there. I see there's a typo. And it's the integral from 0 to 1. So what are they talking about on this one? Imagine if we were looking at the graph of 2t plus 3 quantity cubed, and we wanted to find the area beneath the curve from 0 to 1 of that graph. What would it be? I'm not going to draw the picture of this one. I'm just going to do the calculus. So what do I notice about this? It's not just a number cubed. It's not just, a variable cubed. There's more than that cubed. So what does that mean I'm going to have to do? Most likely I'm going to have to use u substitution. Again, what should I make u? U should be the inside of the function. So let's give it a try. What if I let u equal 2t plus 3? 2t plus 3. If I have u equals 2t plus 3, what do I do for u substitution? Well, I take the derivative with respect to x at both sides. Except, this time it's not the derivative with respect to x, it's the derivative with respect to t. The derivative of 2t plus 3 is simply a 2. Solving for dt, so I'd multiply both sides by dt, divide both sides by 2, I'd have du over 2. Remember, I always substitute in for u. And I substitute in for dt in this case. I rewrite my integral, so it would now be the integral from 0 to 1 of, well, this would be u cubed, and then it would be du over 2. Remember, you can pull out that constant multiple. It's a 2, but it is in the denominator, so I have to pull out a 1/2 integral from 0 to 1 of u cubed du. Now that my variable and my differential match, I'm able to integrate. So that's 1/2. And then I'm going to integrate that. So that would be what? U to the 4th over 4. Usually we would have a plus c. We don't need it because we are evaluating it from 0 to 1. I'm going to go ahead and clean that up. 1/2 times 1/4. So what would this be? It would be 1/8 u to the 4th evaluated from 0 to 1. But here's the big part, never ever forget to substitute back in for u. So when I do that, I would have 1/8 times u, which is 2t plus 3, raised to the 4th, evaluated from 0 to 1. And when I do that, I always plug in the upper limit first. So this is 1/8 times 2 times 1 plus 3 raised to the 4th, Now I need to do the exact same thing, but I need to plug in 0, so that would be 1/8 times 2 times 0 plus 3 raised to the 4th. Plug that into your calculator and see what you get. Looks like I'm getting a total of 64. Okay, so the area beneath the curve of the shape is 64. Now I do want to note, technically what I have written here is wrong. Why is it wrong? The answer is correct, don't worry about that, but I want to get really picky with you guys. Depending on who your teacher is, you might need to be a little clearer about this. What am I talking about? Here's what I'm talking about. When you look at the original problem, your variables in terms of t, and in particular what I want to notice is these limits of integration, that 0 and 1 are in terms of t. So when I go to do my integration, and I have the integral from 0 to 1 of u cubed du over 2, technically that's t equals 0 and t equals 1. Again, every single time you see it, it's t equals 0 and t equals 1. The way that we had it written down, it looks like you could plug in 0 and 1 for u, but we can't. So if we want to do it this way, like we always have, you simply just need to write t equals and t equals every time you see a u until you get it back in terms of t. Then you can drop the t equals 0 and the t equals 1 because we've done it that part. So we could do it just like we did the entire way, except I need to add in those t equals when I see all of those limits to be mathematically accurate, to have those equal signs. Again, some teachers are going to be very much sticklers on this and require you to do this, whereas other teachers will understand what you meant and not do anything wrong, not take any points off. The biggest mistake, though, when you don't put it, is this line right here where it says 1/8 u to the 4th. A lot of students, if they don't write that t equals, they would plug in 1 for u and they'd plug in 0 for u, which would get completely the wrong answer. So by putting that t equals, you tend to not make that mistake. Let me teach you a second way of doing this answer here. So here's a second way of doing this problem, and this gets rid of having to do all those t equals. So what I want you to remember is we said u equals 2t plus 3. That was our original thing. And then remember we had t equals 0. Well, if t equals 0, that would tell me that u equals 2 times 0 plus 3. So that's u equals 3. And then when we looked at t equals 1, which is the upper limit, we would have had u equals 2 times 1 plus 3. 2 times 1 is 2 plus 3 is 5. So that tells me that u would equal 5. So this is my lower limit of 3, and this is my upper limit of 5. So what I could do is go back to that integral. When I rewrote that integral, I'm going to go back to this part right here where I've already substituted it in, so I've done a little bit of work. But I had the integral, and then it was of u cubed, and then it was a du over 2. But instead of writing t equals 0 and t equals 1, I'm going to use u equals 3 and u equals 5. And now I don't need to have the t equals. I can just have those u values. When I integrated it, if you remember, I ended up with 1/8 u to the 4th. And then here I would have u equals 3 to u equals 5. So what this allows me to do is I don't have to back substitute for u. I could just directly plug in the 5 and the 3 for u. So this would be 1/8 times 5 to the 4th. And then I'd subtract off 1/8 times 3 to the 4th. And when I do that, I would end up with 64 just the same. So we have two different options here. The first option is integrate like we've always integrated. Just remember to add the t equals. The second option is change your limits of integration instead of being in terms of t to being in terms of u. I don't care which way you do it, the black way or the blue way here. I don't care if you just back substitute and get it back in terms of t and plug it in, or if you change your limit of integrations to in terms of u and just plug in directly for u. Two different techniques, different textbooks teach you the different ways. I wanted to show you both. Usually I tend to do it the black way, the original way, which is I just write the t equals with my limits of integration, and I'm perfectly fine right there. I do want to point out, if you look at example 2, we didn't need to deal with any of that junk because we didn't have u substitution. The only time you have to deal with this issue is if you use u substitution.